Welcome to Approximation Algorithms and the lecture on random sampling and priority sampling. My name is Rasmus Pagh. We're going to start up with a familiar example, namely how to gather information via polls. Then we'll discuss how to do similar things using algorithms. Reservoir sampling, we'll discuss tail inequalities, weighted random sampling, and finally priority sampling. Consider the two following settings. In the first setting, we make calls to 2,000 random phone numbers. Among those 2,000, 1,000 people respond. 60% of them say that they are going to vote for the current government. And the rest, 40%, say that they will vote for the opposition. Now the question is, what can we say about the general population? How many of them are going to vote for the current government? In the second case, a newspaper calls 100 companies and asks them what the probability is that they are going to make a new hire in 2021. So we get probabilities P1 through P100, and we may ask what fraction of companies among the 100 and overall do we expect will hire in 2021. Take a moment to think about these two questions. To say something about the first case, we need to know something about the response rates or sampling probabilities for the two distinct populations, S of government voters and S of opposition voters. Think about it like this. There are four categories depending on what they vote for and whether or not they respond. There are several different distributions in these four categories that are consistent with the information we have so far. One possible distribution is that actually both government and opposition voters are 50%, but they have different response rates. Another possible distribution is that the two categories actually have the same response rate, and hence actually 60% of the voters are government voters. We can distinguish between these two cases if we know how to weigh the different responses. Let's consider a randomly selected voter X and the set A of voters who respond to the call. By definition, the probability that X is an A, given that X is a government voter, is the probability that X is in A and a government voter divided by the probability that X is a government voter. The former of these two is what we can observe. The latter is what we want to estimate. So if we have an estimate or know the ratio on the left-hand side, well, then we can compute what we want from what we can observe. In case 2, we can think about random variables xi, where xi is 1 if company I hires and 0 otherwise. So the responses from the companies can be interpreted as expectations for this random variable. The number of hires in expectation is simply the sum then of these random variables, which is the sum of expectations, which is the sum of the reported numbers pi. This is the number of hires among the 100. What about the general population? So suppose we have n companies and the 100 are randomly sampled. The expected total number of hires can be expressed, again, in terms of another random variable, yi, where yi is 1 if the company is sampled and 0 otherwise. So then we can simply express this sum over all companies as the sum of probabilities that xi hires and is sampled divided by the probability that I is sampled. This is again the sum of pi's from before divided by the sampling probability, which is 100 over n. Or in other words, we have to multiply by the inverse of the sampling rate. Though this works in the sense of having the right expectation, we are going to see later that it can be improved by using so-called weighted sampling. That's takes samples according to the weight and samples high weight items more frequently than low weight items. A useful tool for understanding sampling algorithmically is the so-called Fisher-Yates shuffle that maintains a random sample of elements under insertions. We store a counter n, which is the number of elements currently stored, and a random permutation of the n elements, say in an array. And we need to maintain this under insertion of new elements. So initially, obviously, we start with 0 elements and an empty array A. When we insert, we increase the counter and add the element to the array. So the first one, there is no choice really, but starting from the second one, we have a choice. We need to decide where the new element should be put. There are two possibilities. Maybe we choose the first one. And wherever we put the new element, we are going to move that element to the new entry that is added at the end of the array. In general, we are going to have some random permutation of the existing elements that we extend to have one more capacity for one more element. We choose a random index for the new element and displace the element at position I, which was chosen, to the last entry. It's easy to show the invariant that A is a random permutation of the elements x1 through xn. How does this relate to sampling? Well, there is a sampling algorithm known as reservoir sampling that can be thought of as simply keeping some of the elements of the Fisher-Yates shuffle. In particular, suppose we keep only the first S entries of the shuffle. Then we have a random sample consisting of S elements. Then moving an element at position I to the last position simply corresponds to discarding it. In distributed settings, sampling is very useful. Think about 3 data sets, A, B, and C, that reside on different computers. And suppose that each of them have taken a reservoir sample of that data set. I claim that we can combine the 3 samples into a single reservoir sample of the union of the data sets, assuming that A, B, and C are disjoint data sets. The reservoir sample we come up with should have size S, and we want the probability of sampling a particular element should be the size of the sample divided by the size of the dataset. Sampling is a very powerful tool for understanding a population without seeing all of it. In order to understand the approximation that we would get using sampling, we have to understand tail inequalities. Suppose we have a bunch of random variables x1 through xn, and the quantity we want to estimate is the sum of these random variables which has some expectation mu. How close is the observed sum to mu? We can think about the probability distribution of the sum over all xi. It has some expectation somewhere in the middle and a distribution of possible values. So one question is, what is kind of the typical deviation? And this is often expressed in terms of the variance. One fact is that most of the probability mass is going to be within an interval of length that is roughly 2 times the variance. In the setting above, if the variables are independent, we can bound that by 2 times the square root of the expectation. Another type of question you can ask is, how likely is it that there's a large deviation? So say that we get less than half the variance or more than twice the variance. These are called tail probabilities, and it's possible to show that in this setting, again assuming independence, that they are exponentially small in the expectation mu. We're going to formalize both of these things on the next slide. The former is called Chebyshev's inequality. It describes the behavior close to the expectation, and Chernoff bounds describe the behavior further away from the expectation. In general, the larger the expectation, the more precise. Let's relate the tail bounds to approximation and also make things a little bit more precise. Chebyshev's inequality says that the probability that x deviates from its expectation by more than k can be bounded by the variance divided by k squared. In terms of approximation guarantee, if we assume that the variance is relatively small, which is often the case, that it can be bounded, for example, by the expectation, then the probability that x is reasonably close, let's say between 1/2 of the expectation and 2 times the expectation, is good. So it's roughly 1 minus 4 over the expectation. So this is just an example of what you can get by Chebyshev. In general, it gives a whole trade-off between accuracy and probability. The Chernoff bound gives considerably better bounds if we are far from the expectation, and also tells us something quite close to the expectation. So again, remember that we are considering a sum of random indicator variables. The probability that we get something that is a factor either 1 minus epsilon, at most 1 minus epsilon times the expectation, or 1 plus epsilon times the expectation, is exponentially small in the expectation, as I claimed before. And the constant in the exponent is related to epsilon squared. So for the upper side, it's epsilon squared over 2, and for the lower side, and for the upper side, it's epsilon squared over 4. And there are different variants of this. In terms of approximation guarantee, we see that if the expectation is more than 4 log 2 over delta divided by epsilon squared, then we get that x is in the interval 1 minus epsilon times the expectation to 1 plus epsilon times the expectation, with probability at least 1 minus delta. Now let's turn to a different kind of random sampling in which we want to take element weights into account. So we have a bunch of items that each come with a weight. Let's say that the item I comes with a weight wi, which is non-negative. What we want to do intuitively is to sample higher weight items more frequently than lower weight items. And this is in order to simply gather more information about high weight items. So let's look at a small example. So we have our weight distribution here, a bunch of items with different weights. So suppose we just want to sample a single item. Then there's a very natural thing one can do. So we can sample item I with probability wi divided by the sum of all weights. So this gives a sampling probability proportional to the weight, which is nice. And the normalizing factor down here ensures that this is actually a probability distribution, that we get one sample in expectation. But if we want to sample 5 elements, we want to sample all of them. So how does this look in general? So let's consider a general sample size S. So the idea here is that we find some cutoff points, which we call tau, such that if we sum the minimum over all weights of wi over tau and 1, we get exactly S. So in the case where we sample all, this corresponds to tau equal to 0. The minimum will always be 1. And in the case where we sample just a single item, it corresponds to tau equal to the sum of all items. But in general, tau will be somewhere in the middle, where there are some weights that are above tau, and they will be included in the sample with probability 1. And there are some elements that are below tau, and they will be included in the sample with probability, which is the weight divided by tau. And it's easy to see that if we do it like this, the expected sample size is exactly S. So let's call this sampling probability Pi, minimum of 1 and Wi over tau. When we do weighted random sampling, we are often interested in computing some function of the weights. Simplest case here is when we're interested in the sum over some set of items of the weights. And it's important to stress this set is not known before sampling, so we cannot really adjust the sampling procedure based on the knowledge of the set. Let's call this set Q. One thing that we can do from the sample is to compute the sum of weights of those elements we have actually sampled. So in order to get an estimator of every items, the sum of weights of all items in Q, including the ones we haven't sampled, we can use the estimator U hat, which is simply the sum of the sample weights divided by the sampling probabilities. Now I claim that the expected value of mu hat can be written as a sum over I, all I, of the probability that I is in the sample multiplied by Wi over Pi. So this is the sum over all items in Q. So why is that? Well, to see this, write the definition of mu hat in a different way. We sum over all I in Q, an indicator variable that I is in S, multiplied by Wi over Pi. The expected value of the indicator variable is exactly the probability that I is in S. Altogether, this means that the expected value of mu hat is exactly mu. And we can use mu hat as an unbiased estimator. An important property of weighted sampling is that it gets the smallest possible variance among all sampling methods that use space S. The estimator that divides by the sampling probability is also known as the Horwitz-Thompson estimator, and it's an old technique from statistics. In the book, it's described how one can do efficient updates and merges of samples that are weighted. Details are a bit complicated, so I refer to the book for those. The final topic of this lecture is priority sampling, which is a simpler way of doing weighted random sampling. The idea is to assign to each element a priority. So item X gets a priority Qx that is computed as follows. We sample a random value, alpha x, in the interval 0 to 1 uniformly. Then Qx is simply the weight divided by alpha x. So we see that higher weight elements tend to have higher priorities, but even low weight elements can have a very high priority. Now the sample is simply the S items that have the highest priorities. This is extremely simple to implement. In order to give an estimator, we need to define the threshold, which becomes equal to the S plus first highest priority, so the highest priority that is not sampled. And we can maintain the sample and also the threshold using a priority queue. Now the estimator, unbiased estimator U hat, is again a sum over all the samples in the set Q that we care about, and what we sum is the maximum of 1 and the weight Wx over tau, this threshold. Now I claim that this is an unbiased estimator. That is that the expected value of mu hat is exactly the weight of x, if this is for the case of a single element. And even something stronger is true, namely that the expected value of mu hat given a particular value of tau is equal to Wi. The full proof is in the book, but let me illustrate why this is true. So suppose this is the weight distribution. Now the priorities are given by dividing by a number that is less than 1. So the priorities will be greater, sometimes much bigger, sometimes just a little bit bigger. Let's define a value tau prime, which is the S highest priority. And let's look at a new element x. So t prime is the third highest priority in this example among other elements than x. Now there are two cases to consider. First, if Wx is greater than or equal to tau prime, then it doesn't matter what alpha x is. X will end up in the sample with probability 1. Otherwise, if Wx is strictly less than tau, So this is the case here. Then, depending on the value of alpha x, we may or may not end up in the sample. And if you work it out, it turns out that x ends up in the sample if and only if alpha x is less than wx over tau, which happens with probability wx over tau. Priority sampling is due to Duffield, Lund and Thorup, the latter two which are Danish, and Mikkel Thorup is even a professor at University of Copenhagen, so you may know him from other courses. It's known to be optimal up to a single sample, in the sense that a priority sample of size s plus 1 is at least as good as a weighted random sample of size s. Welcome to Approximation Algorithms and the lecture on cardinality estimation. My name is Rasmus Pagh. Today we'll start by looking at coordinated sampling, also known as KMV summary. And we're going to look at an application in distributed counting. Then we'll talk about the hyperlog sketch, that is also a cardinality estimation method, and look at an application in estimating graph neighborhoods. Finally, we'll look at Bloom filters and an application in estimating set intersection sizes. Last time we looked at random independent samples. These are good for many things, but not for everything. One issue is that it's unlikely when we do two independent samples that the same elements appear in both of them. Suppose, for example, that we sample from two overlapping sets, A and B. From A we sample a set SA, and from B we sample a set SB. Now, if the sampling probability is low enough, these independent random samples are unlikely to contain any elements from the intersection, or at least there will be very little information about A intersection B. The idea behind coordinated sampling is to make the decision of whether to sample an element or not dependent or coordinated by basing it not on an independent random choice, but on a random hash value h of x that is the same for every sample that you take. Such samples are also known as consistent samples. Let's denote them by S prime A and S prime B. A particular way of doing coordinated sampling is the k-minimum value or KMV summary. To construct such a summary, we pick a random hash function h that maps to some large range of size r. So here all that matters is that r is large enough. So we could pick it to be 2 to the 64 or some other large values such that we have very few collisions. The sample now consists of pairs of elements x and corresponding hash values h of x that have small hash values. In particular, we store the k smallest hash values where k is the space we have available. So let's illustrate this for A and B. So we order the elements according to the hash value, and let's suppose that we want to produce a sample of size 5. Then we simply start with the lowest hash values and pick the 5 smallest hash values from A and the corresponding elements, and similarly for B. Okay. So we are basically going to store all the elements and corresponding hash values below some threshold. This kind of coordination makes it more likely that we are going to catch or sample something from both A and B. Observe that the threshold can be different. So in particular, it might be that there's some element in the intersection that is included in one sample and not the other one. So in that sense, the sampling is not fully consistent if we fix the size of each sample. So what are the properties of KMV? It's easy to see that you can efficiently update it. You can maintain a priority queue and even do smarter things to get logarithmic or even constant time updates. Also, you can merge two KMV summaries in linear time by eliminating duplicates and computing the median. Finally, and this is not obvious, we can take these sketches and estimate the set cardinalities. Okay. So the way this is done is that we look at the largest hash value among those stored. So remember, we store the k smallest hash value, and we take the largest one among those. So this would be the kth smallest among all hash values. Now we can compute an estimator n hat, where n is the size of the set, as k minus 1 times r, this range, divided by this hash value vk. That turns out to be a good estimator for the size of A, which we denote by n. So the intuition is the following. Let's look at all the possible hash values between 1 and r. And we can think about the distribution of these hash values. Well, because the hash function is supposedly random, these are close to evenly distributed. And if we look at a particular interval, for example, the one between 1 and k minus 1 over n times r, we can compute how many elements are expected. And for this particular element, or this particular interval, the expected number of hash values is k minus 1. So this means that if we take the kth smallest hash value, it's likely to be just to the right of this interval. So that is, it's a good estimator for the location of this interval. And now we can solve for n and get our estimate of n based on the observed value of vk. The formal argument uses Chebyshev's inequality twice to bound the probability that there are unusually few or unusually many small values among the hash values. It can be shown that if we choose k to be O of 1 over epsilon squared, then we get a relative error of 1 plus minus epsilon with constant probability. Let's consider an application of this summary. Suppose we have a bunch of sets, A1 through AM, and all of them are quite large. What we can do is construct a summary for each of the sets, and we can potentially collect them. Even if these sets are distributed across many machines on the internet, we can compute these relatively small summaries of maybe a few thousand elements each. Let's call those SA1 through SAM. Since these summaries are mergeable, we can merge them to form a summary of the union of these sets. So here it's important to note that this summary depends only on the set of elements that exist in the union, not on the multiplicity. So if an element appears several times, we're simply going to eliminate any duplicates that we see. Now we have a summary of the union. We can use it to estimate the size of the union with small relative error. In terms of k, it's 1 plus minus O of 1 over square root of k. And this is going to work with constant probability. If we want something more certain, we can use repetition and take several estimates and take the median to get an estimate that we are quite certain is true. So if each estimate is accurate with probability 3/4 and we take the median of roughly log 1 over delta estimates, then it's easy to show using Chertoff bounds that the probability that we get a bad estimate in the median can be bounded by 1 minus delta. Finally, if we are interested only in certain elements in some sets Q, we can also estimate the intersection size of A and Q by looking at the elements in the merge sketch that belong to Q. The hyperlog log summary is a space-efficient alternative to the k-minimum value sketch. It doesn't keep a sample, and in particular we don't know what are any of the elements in the set, but it does support insertion, merging, and cardinality estimation. The idea is to combine a lot of crude estimators of cardinality. And each of these estimators should use only a small number of bits. An observation we can make is that we can crudely order hash values by the number of leading zeros in the bit representation of the hash values. So, for example, here h of x has 3 leading zeros, and we'll denote this number of leading zeros as set of the hash value h of x. Another hash value might look like this, with a 1 in the first place, so set of h of y is 0. So just storing the set value rather than the hash itself is cheaper than storing the hash. So if the hash is order log n bits, for example, we can store the number of leading zeros in the logarithm of that, which is log n plus a constant number of bits. In practice, log n for any reasonable value of n is something like 6 to 8. Let's look at the details of how this works. We're going to use two hash functions. Let's call them h and g. Here h has a range of size k, which will determine the space usage, and g has a large range, let's say w-bit numbers, where 2 to the w is much larger than n. The sketch consists of a sequence or array of k counters, where the ith counter is a crude estimate, or can be used to form a crude estimate for the set of those elements in A that hash to I under H. So, and specifically, Ci is simply the maximum of the number of leading zeros of g of x of all elements x that are in AI, that hash to I under H. It's easy to see that we can update this under insertions, and also we can see that if we want to merge two sketches, call them C and C prime, we can do it by simply taking coordinate-wise maximum of the values. And what we'll get out of this is exactly identical to a sketch in which all the elements that were ever inserted in either C or C prime were inserted. Now the question is, of course, how do you use this information to estimate the number of elements inserted, the number of distinct elements? And one thing we can observe is that if we look at the ith counter, actually the largest hash value in AI is going to be roughly 2 to the w minus Ci, because we know that there's a bit in position Ci from the largest value. This means that we can estimate the size of AI using the reasoning from KMV as 2 to the power Ci. We could extrapolate and estimate A as simply the sum of all these estimates. Unfortunately, this estimator is going to be very sensitive to just a few large counters. It turns out, so this is a first attempt, it turns out that you can do much better combining these counters in a different way. The idea is to take the harmonic mean instead of the arithmetic mean of these estimators 2 to the Ci. And this is a much more outlier robust method. And the details are relatively complicated, so I refer to the book for those. One can show that the average relative error is going to be very small, approximately 1 divided by square root of k. Hyperlog has lots of applications and is used extensively for analyzing large data sets. One of the cutest applications I know is ANF, or approximate neighborhood function. The setting is that we have a large undirected graph, vertex sets V and edge set E. We consider the case where the number of vertices and edges is really large, maybe 1 billion and 100 billion edges. This is still a pretty sparse graph in the sense that the number of edges is much smaller than the number of vertices squared. What we want to do is to compute for every vertex V the average distance, the average shortest distance to all other vertices in V. If you like, the distance distribution of every vertex. This only makes sense if it's a connected graph, so let's assume that. A baseline algorithm, what you could do after your first algorithms course, is to run breadth first search from each vertex, so that's size of V times. But this is, for such a large graph, this is just unfeasible. Definitely on a single machine, and even with parallelism, it's challenging. An alternative is to look at sets. Let's define SIV as a set of vertices at distance at most I from vertex V. It's easy to see, or by definition almost, S0V is just V itself, and we can inductively define Si plus 1V as the union over all neighbors of V of SIW for neighbor W union with SIV. Now we can use this in combination with HLL. So if we know HLL for distance at most I, we can merge them to compute HLLs for sets of vertices of distance at most I plus 1, just using the above recurrence. And all of these merges, it's easy to see that they can be computed efficiently. We basically just need to do work across each edge. So in basically number of edges merge operations, we can do this, and each merge costs linear time in the side of the sketch. And we can repeat this to compute these estimates for different values of I. If the graph has small diameter, then it suffices to do this for a small number of iterations, and we'll have found all the relevant information to compute the average distance. The last part, we're going to look at Bloom filters. I'm going to describe a variant of what is in the book called split Bloom filters that I think are slightly easier to understand. Bloom filters are an approximate version of a hash set, if you know that from Java, that stores a set of keys. You can insert elements just like in a hash set, and you can ask about membership. So a query for a set or for an element X. Let's call the set of elements that have been inserted S. A query is supposed to answer yes or 1 if the element is in the set. A normal dictionary, you would answer 0 whenever the element is not in the set. But now things are slightly different. With some probability, epsilon, we may not answer 0 if X is not in S. So with probability at most epsilon, it's acceptable to answer 1 or yes, even if X is not in the set. And with the remaining probability at least 1 minus epsilon, we answer 0. So here epsilon is a parameter that determines how often these false positives, where we answer yes for something that is not in the set, occur. It turns out that this can be done with space usage that is just O of n log 1 over epsilon bits. So for each element in the set, we pay just log 1 over epsilon bits, which is often much less than what is required to store the elements in the set itself. Split Bloom filters work as follows. So let's define the space usage as, or denote the space usage by n. We're going to use k hash functions for some parameter k. each of which map elements to one or to a range of size m divided by k. So 1/k of the space usage, and we are going to have k bit vectors that each use m over k bits. So total space is m bits. So the bit vectors look something like this. The way we insert an element into the split Bloom filter is by evaluating all of the hash functions and using them to index the respective bit vectors. And we simply put a 1 in all of those positions where x hashes to. So in the end we are going to have a 1 in exactly those positions that some element hashes to. Some positions might have 1s set several times, of course, but that's fine. Okay. So what about queries? So suppose we query for some element y. We're going to do almost the same thing. We're going to evaluate all of the hash values, and we're going to look in these bit vectors. If we see a 0 somewhere, then we know that for sure y cannot have been inserted, because then we would have placed a 1. In this case, it's safe to answer no or 0, because we can only do that if we know for sure that an element is not in the set. If it happens that all of the hash values that we look at, all the bit positions that we look at are 1, then it might be that y was inserted. It could also be that we just had hash collisions with things that were inserted, and then we answer 1 or yes. So one parameter choice that works, it's not the best one, but it's close to optimal, is to let k be the logarithm base 2 of 1 over epsilon, m 2kn, which is 2n log 1 over epsilon. So why does this work? Well, we need to analyze the false positive probability. So suppose that y was never inserted. What's the probability that we actually have a value of 1 for every I in position hi of y in bit vector bi? By independence, this is just a product of these probabilities. And in each table, we know that there is at most n entries out of the 2n entries that are 1. So each of these probabilities is bounded by 1/2, and the product is bounded by epsilon. One thing to note here is that in order to set the parameter m, we need to know n, or at least a bound on n in advance. One application of Bloom filters is estimating the intersection size of large sets. Or if you like, the number of common elements. Let's consider a very large set A and a smaller but still very large set B. Okay, so the question, so here they're drawn without an intersection, but they do have some intersection. The question we can ask is, how large is the intersection of A and B? And it may be that both sets actually don't fit in memory of your computer, but you can fit the smaller one into memory if you create its Bloom filter. Okay, so the Bloom filter itself fits in memory. So now what we can do is scan over A, which is presumably stored on some kind of storage device, and for each element in A, you look it up in the Bloom filter for B. And you get some number of positive answers. So now you know that the false positive rate is going to be epsilon, so we can estimate the number of common elements as the number of positives minus the expected number of false positives. Welcome to Approximation Algorithms and a lecture on summaries for multisets. My name is Rasmus Pagh. We'll start the lecture with a motivating example about website statistics. Then we're going to look at two summaries, the misogrees summary and the count min summary. Let's consider a data set which consists of a log from a browser. We have a bunch of timestamps and corresponding websites that were visited at those times. One type of question that you might want to ask about these kind of data is, what are the most popular websites? You could measure popularity in several different ways, for example in the number of page views or in the total amount of time spent on a page. Of course, if this is just data coming from one machine or one user, this is pretty small data and it's easy to solve. But what if you have a billion users? Then we have a big data problem. The goal that we will discuss in this lecture is how to answer such questions using sublinear space. This improves on the trivial solution, where you just use a dictionary to keep track of the mapping between websites and counts. For big data problems, linear space is just not feasible. The Mr. Grease summary works in the following setting. We receive a stream of pairs consisting of an item X and a corresponding weight W. Let's call the stream S. It's important to notice that the same item can appear several times in the stream. The weight of an item is defined as the sum over all weights with which this item occurs in the stream. The Mr. Grease summary consists of k pairs, where k is a parameter that you can set. Each x is associated with a weight wx, which is supposed to be an approximation of the true weight. Since we are not able to store all pairs, the weight that we store is not necessarily equal to the true weight of x in S. To distinguish these two, we denote the true weight by wx star. We need to be able to maintain this summary under updates, that is, new elements in the stream. Also, we want the ability to merge two summaries into one of the same size. The merged summary should reflect the multiset union in the sense that the weight of each item should be the sum of the weights in the two summaries. So if the two summaries are S1 and S2, the true weight in the combined summary is simply the sum of the weights in the two summaries separately. Next, let's look at how the Mr. Grease summary handles updates. We consider the case of k equals to 3, and for simplicity, all weights are equal to 1. Suppose the input stream starts with an A. The data structure consists, as we said before, of an array of items and corresponding counts. Let's call it T. Since there is space, we simply insert A with a count of 1. Then we see B in the stream, and it also is inserted with a count of 1. When we see A again, we update the counter so that it's equal to 2. When we see C, we insert it with a count of 1. Now comes a new element D. There's now no space in the summary to just put in D, so we need to do something. What we'll do is to say that the smallest counts must go. This is going to give the smallest error, or the smallest difference between what is stored and the true counts. We're going to subtract the minimum count, which is 1, from all the counts. So these are the revised counts. And now we can evict or kick out all of the elements with 0 counts. So we do that. We also insert D, and kind of for technical reasons, we also subtract M from the count of D, so it ends up with a 1. We go on like this for a little while. It may be that we again have an element where there's no space, and we do the same thing. We subtract the minimum from all the counts, throw out the elements with 0 counts, and insert the new one with M subtracted. And it goes on like this. So now the question is, how big an error can we make here? Before we go on and answer that question, let's state the general insertion algorithm based on this example. So of course, if an item X is already in there, we simply increase the counter by W. Otherwise, if there is a free slot, that's a slot with a count of 0, then we can simply override that and write the pair X, W. And finally, if there's no space, we are going to decrease all the counters by M, which is the minimum over all weights in T. And then we're going to insert the new pair, which consists of X with weight W minus M. Now I want you to pause and think. So we saw a way to insert. What about merging? Suppose we have two empty summaries. How do we merge them into one of the same size? Let's analyze the error made by Mr. Gries. A first observation we can make is that it's always going to be the case that the weight we record is less than or equal to the true weight. Why is that? Well, every time we increase the weight that we store, we see an occurrence of the element with that weight in the stream. So we can never have a weight that is increased without actually having a corresponding element in the stream. Second, we claim that the stored weight cannot be too much smaller than the true weight. The difference is the L1 norm of the true weight vector divided by k plus 1, where the L1 norm is defined as the sum of absolute values of the entries. Here we are going to assume that all the entries are non-negative, so the absolute value doesn't really do anything, but that's the general definition. How do we argue for the lower bound on Wx? Let's consider the sum of all weights that we actually store in the sketch. So that is the sum of Wx for all elements x in T. Now we have a stronger claim, namely that Wx is going to be at least the true weight of x divided by the L1 norm minus m divided by k plus 1. So here the L1 norm minus m can be thought of as the total weight of the discarded elements that are not present in the sketch. So what happens when we update? And here we are going to focus on the case where there's no space in the sketch, and we need to insert a new element x, w. That is where x is not in T. Let's denote the new value of m by m prime. So we are going to subtract the minimum m from k plus 1 values, the k ones in the sketch, and the new element. And we're going to add the weight w. The new weight that is going to be stored is the old weight minus m, and the induction hypothesis tells us that this is at least equal to the old weight vector minus the old m divided by k minus 1, which again by definition is equal to what we want, namely the weight of the new weight vector minus the new value of m divided by k plus 1. Of course, we also need to consider the case where the element x actually is in the summary, but in this case it's really easy to see by induction that the claim holds. For merge, we can also make an argument that all the weights are close to the true weight, and I refer to the book for that. Let's try to plug in some concrete numbers. Suppose that we are storing information about 10 billion website visits, that's 10 to the 10 websites, and we have just a laptop. So we have capacity to store, let's say, 10 million URLs and corresponding counts, 10 million pairs. So k is 10 million, and the number of visits is 10 to the 10, so then the error in the number of visits recorded is at most 1000. In practice, one can often get a much better error by some variants that I'm going to discuss next. So there's a bunch of variants of misagrees. One variant is to keep track of the highest weight you have seen for each item, x. So you do subtract from the weight, but you also keep track of the highest weight. This is a heuristic to decrease the error in typical cases where entries with high weights stay in the sketch for a long time. You can also keep track of the L1 norm of the true vector count to support upper bounds on the true weights, using the formula that the true weight is at most the stored weight plus the L1 norm minus m over k plus 1. So in this way we are going to have both lower and upper bounds explicitly stored. Finally, it's possible to give some support for negative updates by simply thinking of negative and positive updates as affecting several separate variables. So instead of thinking as a true count as one variable, we think about it as a difference between two non-negative variables. And we put both of these values into the sketch and estimate the true count of negative updates and the true sum of positive updates. The so-called space-saving algorithm is a variant of misagrees that was independently discovered that keeps track of upper bounds rather than lower bounds. It's discussed in section 3.3 in the book, where they also argue that it's actually equivalent to misagrees in the sense that one can be translated to the other. Now let's go to something related, but using very different techniques. So in school, you probably learned about histograms. So histograms record a number for each item in some set. So it's closely related to what we're looking at here. So a histogram could look something like this for website visits. So you have like a column for each number that you care about, and you put them next to each other. So clearly the space for storing such a histogram depends on the number of distinct things you want to count. So the number of distinct items. And obviously this can be pretty large in the case of websites and so on. But what we can do, and which is actually often done, just to reduce the space for such a histogram, is to lump things together. So here you could lump search engines together, social media, education, and so on, and you're going to get a much smaller histogram that gives you at least some information that is relevant. But the question is how to choose the categories. What we're going to discuss next can be seen as a randomized ways of choosing the categories. So instead of kind of semantic categories as in the example, we are going to use hashing to categorize or put counts in different of these columns. So this means, of course, that any semantic meaning is broken. So google.com might end up in a different column than bing.com. But we can ask what kind of approximation can we get using these kinds of randomized histograms. So let's discuss one particular way of implementing randomized histograms known as the count-min sketch. And you should note that the notation that we're going to use here on the slides is a bit different from the book. The book also has concrete hash functions that they suggest, but here we're just using general abstract hash functions. So the data structure looks very much like a split Bloom filter. We have D arrays of some size t each. Let's call them C1 through CD. An update with x, w evaluates D hash functions indexing each of the D arrays, and the update simply takes each of these array entries and adds the weight w to each of them. So that is for I equals 1, 2, 3 up to D, we increase Ci of Hi of x by w. The weight update does not actually need to be greater than or equal to 0. It's perfectly possible to do negative updates, which correspond to decreasing a weight. A query proceeds pretty much the same way. We evaluate the hash functions, look up the values, and we look at the weights that are reported in there. And it's easy to see that what we get is going to be the true sum plus some contribution from other elements. And the elements that we get contributions from are those that have hash collisions with x. Let's call this sum the noise sum. What we're going to return is the entry that has the smallest noise. So that's the minimum over all I of ci of hi of x. So this is going to be equal to the true sum plus the minimum of all the noise terms. So that we are allowing negative updates, we are going to assume that the noise is not negative. Now, before we go on, I want you to think, how can we take two count mean sketches and merge them? Also, can you remove one sketch from the other, in the sense that if we know that all the elements that were inserted in one was also inserted in another, can you remove the contribution of the other sketch from the first one? Let's analyze the accuracy of the count mean sketch. We are going to assume that all the true weights are non-negative. So that is, the L1 norm is actually equal to the sum of the true weights. So this assumption is needed for the simple estimator, but it's not needed in general. It is possible, as we'll discuss later, to have an estimator even without this assumption. Now we define Wx hat to be the estimator of the true weight, and we want to bound the difference between Wx hat and the Wx star, the true weight. And as we argued earlier, one is equal to the other plus all of these noise terms. And since all the noise terms are non-negative, this is clearly always going to be an overestimate by our assumption. Let's bound the expected error in table number I. So the expected value of, or the expected sum of all y that collide with x is going to be a weighted sum where we weigh each wy star by the probability of a hash collision, which is exactly 1 over t if we assume random hashing. So all in all, we get something that is bounded by the L1 norm divided by t. Now, Markov inequalities say that it's not too likely that we are far above the expectation. In particular, the probability that we are above 2 times the expectation is at most 1/2. Note that this means that with probability at least 1/2, we get an error that is similar to that of misreagrees with k equals to t. That is roughly the same space usage. But the repetitions allow us to give a better probability bound. So what we really want to estimate is, or bound, is the probability that the estimator differs from the true count by twice the expected deviation for each of them. So this happens since we take the minimum if and only if we have such a large deviation for all I from 1 to d. Now these are independent because we have independent hash functions. So this probability is simply the product of all the probabilities that we have a large deviation in each. And we just argued from Markov that each of these probabilities is at most 1/2. So we have 1/2 to the power d, or 2 to the minus d. Now if you want a particular error probability delta, we simply choose d to be the base 2 logarithm of 1 over delta. And then we succeed with probability 1 minus delta. It's instructive to compare the properties of count min and misreagrees. The space usage for count min is d times t counters, and misreagrees it's k, but it's k pairs. So the unit is different. The error bound for count min is twice the L1 norm divided by t, and for misreagrees it's the L1 norm divided by k plus 1. count mean has an error probability of 2 to the minus d, whereas Mr. Grease is deterministic and doesn't have an error probability. Or if you like, it's 0. But count mean has an advantage. It allows subtraction, so you can basically eliminate the effect of an insertion. This is because it's a so-called linear sketch. Mr. Grease does support some kind of deletions, but the data structure deteriorates with the number of subtractions. So it's not a good data structure if you're going to have a lot of subtractions. Finally, let's discuss how to create an unbiased estimator based on count min. The version we discussed is always going to underestimate the true counts. The idea is to subtract the expected noise from each of the estimators. What we can observe is that the expected noise is the same as the expected value of any other entry in the count sketch. So any Cij where j is different from the hash value of x. So that is, we can look at the estimator that takes Ci hi of x and subtracts some other entry in the sketch from this. And the expectation of that is going to be exactly the true weight of x. Now we can combine several of these, not with minimum, because it's no longer the case that we have positive noise, but we can use the median. So it's possible to show that with high probability, again exponentially small in d, error probability, the median is going to be close to the expectation with high probability. A particular implementation of this idea is a so-called count sketch, which is described in the book, but is not part of the curriculum for this course. Welcome to Approximation Algorithms and the lecture on summaries for ordered datasets. My name is Rasmus Pagh. We'll start by looking at a motivating example and then look at several solutions to summarizing ordered data. QDigest and dynamic count min are both for the case where data is from a fixed domain, whereas the KLL summary works for any ordered domain. As a motivating example, consider a set of timestamps. This could, for example, be clicks on web links. We want to be able to approximate the number of timestamps in a given time interval. A classical approach of summarizing data of this form is to use quantiles. Suppose there are n elements and consider them in sorted order. To construct the quantiles, we take every epsilon n elements and store them. For example, if we set epsilon equal 0.1, we get the 10%, 20%, up to 90% quantiles in this way. The quantiles require linear space to compute, but only 1 over epsilon space to store. Now consider the rank x of an arbitrary element in the domain x, which is defined as the number of elements in the set less than or equal to x. We can approximate the rank from the quantiles with an additive error of at most epsilon n. We want to achieve something similar while using space close to 1 over epsilon. There are two settings to consider. One is where S is a subset of a fixed domain, say 0 to u minus 1, and the other one, S can come from any ordered set. So we'll consider the former first and the latter in the last part of the lecture. But before we go on to discuss the summaries described in the book, let's consider why we don't just use sampling, right? So we saw last week that sampling is a powerful primitive for estimating all kinds of things. We can take a random sample from S, and intuitively it would kind of spread relatively evenly across the range. And we could use this to try to estimate ranks. So in particular, if we look at the random sample R, the expected number of things that are less than or equal to x is going to be some number times the rank of x. And this number is k over n, where k is the size of the sample and n is the number of elements in the set. Inverting this, we could approximate rank as n over k times the rank in the sample. In the exercises next week, we're going to see that this doesn't give as good as a solution as we would like. So the size of the sample needed to make this work is considerably larger than 1 over epsilon. So first we consider the so-called Q-digest summary. Here the assumption is that the elements of S come from this domain of integers from 0 to u minus 1. And we're going to assume that u is a power of 2, and this is without loss of generality. If u is smaller, we could simply round up to the next power of 2, and that would cost us essentially nothing. Now, to describe the data structure, it's instructed to imagine a complete binary tree with u leaves. So this is not actually going to be stored, but this is just a conceptual thing. So here it is for u equal to 8. So the idea is to store in some of the nodes in this complete binary tree counts of elements that appear in that subtree. So the leaves, of course, correspond to all the possible elements of the set. If we have a count in a node, we don't actually know exactly where this count comes from. So to avoid making too large mistakes in the rank bounds, we want to avoid storing counts that are too large. So we are going to limit the counts that we can store to some number c, which is a parameter. So suppose we insert 2. We try to store the count as high as possible under this constraint. Okay, and in this case, an empty data structure, we can store it all the way up in the root node. Okay, so let's consider another insertion, maybe 3. We go up as high as possible. We could store it in the root node. And here I'm just using unary counters because it's easier to draw. So let's consider another insertion, and now let's actually set the value of c to 3. We have another 2. It's also recorded in the root. Now we have a 5. So we cannot insert that in a root because that would violate the maximum count. So we have to insert it one level below. There would be overflow in the root, so to speak. So we go down to the next level and put it in the right child of the root. Similarly, if we insert 0, it also goes to the left child of the root, and so on and so forth. One thing that can happen is that everything is full all the way down to the leaves. So we make an exception to the rules. Leaves may contain counts that are bigger than c. This is not a problem because for leaves we have exact information. We know exactly what this corresponds to. Now, I would like you to think about how this can be used to estimate rank of x, and also what is the error in terms of c and u. The way we have described it, the Q-digest can grow quite large. So there's a need to reduce the size. The value of c needed to ensure an epsilon n error is epsilon n over log u. This grows with n, which means that capacity can arise as the number of elements grows. We can observe that if most of the nodes are within a constant factor of capacity, then we actually only need log u over epsilon nodes, which is only a logarithmic factor from the size of the quantiles. So we somehow want to ensure that most of the capacity is actually used. So initially we might have c equals to 3, but at some later point with more elements inserted we might have c equals to 6, and we want to, a lot of nodes are suddenly underfull and can have more capacity. So the idea is to compress the data structure by moving counts up. Okay, in such a way that if your parent is not full, you move a corresponding count up in order to fill it. And this may empty some nodes and save us space. So the invariant after the compress is that all nodes that have a count, non-zero count, less than c, have a parent with count c. And this means that the total number of nodes is going to be with non-zero counts is going to be O of n over c, as we wanted to. If we do this periodically, we can maintain order of n over c non-zero counts at all times. The next summary we are going to look at is the so-called dyadic count-min sketch. In the book, there is a discussion of the dyadic count sketch, which is exactly the same thing, except that count sketch is used rather than count-min, but it works essentially the same way. The idea is to use a count-min sketch to compress the counts in a complete binary tree. So let's consider the complete binary tree. Each time we insert something, we are going to record the count at every level above. Okay, so before it was only represented at some level, but now we actually add to a counter at every level all the way up to the top. So we can have a lot of non-zero counters. So this would be a problem if we stored it exactly. But what we can do instead, if we index the nodes in some way, for example using binary strings, that we can store the counts in a sketch. On an update, we want to increase the counts of all the nodes on the path to the root from the leaf corresponding to the inserted elements. This corresponds to all prefixes of the binary representation of the element. So trivially, if we would just store this directly, we would need to store the number of distinct strings, which could be huge. But with count-min, we can basically decide the space ourselves, and we are going to get an approximation of the counts. We want to choose the space such that the error is at most epsilon n over log u, and each estimate should hold with probability 1 minus delta over log u as well. If we can do this, then we can use a similar technique as before to estimate the rank of any element in the set. If you work it out with the L1 norm of the dataset we insert, it's at most n times log u, because we insert log u elements for each in the count-min sketch for each insertion, and the space works out to be a polylog factor times 1 over epsilon. And as I said, this uses the fact that the sum of all weights is n log u. This is not a tight bound, it can be improved, and you can see the book for that. Next we are going to look at the so-called Carnot-Lang Liberty or KLL summary, which has become quite famous and widely used for summarizing ordered data. It works with any ordered domain, so it doesn't have to be integers in some range, and this also means that we are not going to get the dependence on the log of the range size, as we saw before. The data structure is a sequence of lists, also called buffers, that are each stored in sorted order. So the sizes of these lists are geometrically growing, and we have a total number of h plus 1 levels numbered from 0 to h, and each level is a factor of 1 over c bigger than the previous one, where c is a parameter between 1/2 and 1. And this is of course approximate because the actual sizes are integers, but we'll assume that they grow by a factor exactly 1 over c, except the lowest levels. So we might go down to size 2, and we won't go any further down. So the intuition is that elements at level L are going to represent 2 to the L elements in the input. We can insert new elements at level 0, corresponding to 2 to the 0 elements, and then we are going to move up elements to the next level when the level is full. And this is a so-called compress or compaction step. And what we need to do here is to discard half of the elements. In this way, each element that moves up corresponds to twice the number of elements as before. So let's look at an example. Let's suppose we have a buffer at some level with, in this case, 8 elements. Now we are going to choose between two possible lists of elements to move up to the next level. So either we take all the odd-numbered elements from the list in sorted order, or we take the even-numbered elements from the list. So it's some kind of sample, but it's kind of highly structured. So let's think about how this affects rank. So we start with elements that each represent 2 to the L, or have weight 2 to the L, and we want to end up with elements that have half the number of elements that each have weight 2 to the L plus 1. If we think about an element that has even rank in the original list, then the rank with respect to that list is going to be 2i for some I times 2 to the L, where 2 to the L is the number of elements represented by each element. When we do the compression step, the rank is going to remain the same. It's still going to be I times 2 to the L plus 1, both in the odd and the even numbered case. On the other hand, if the rank is odd, in the sense that we have an odd position in the list, and then of course multiplied by 2 to the L, then we get different ranks in the two cases. So if we choose the even numbered things in the compression step, we are going to get a rank of I times 2 to the L plus 1. And if we choose the odd numbered case, it's going to be I plus 1 times 2 to the L plus 1. So both of these are wrong. One is slightly too small, one is slightly too large, but on average they're actually correct. So now the idea is to choose this at random. Then we are going to get the correct thing in expectation. So the general picture for KLL is as follows. So we have our h plus 1 levels of buffers. Let's call them B0 through BH. And remember that at level L, each element represents 2 to the L input elements. To get an estimator for the rank of X, we simply sum up estimators for the ranks represented by each level. So we sum over all levels, and we take the number of items at that level less than or equal to X, weighed by 2 to the I for level I. And because of the unbiasedness of the compaction step, this is going to be an unbiased estimator. So far, I only told you that the sizes of the buffers are going to grow geometrically, but we need to specify exactly what size the largest buffer should be. And here we introduce a parameter k and ask that the largest buffer has size k divided by c to the h, where c was this parameter between 1/2 and 1. And we'll talk about how to set k later. So now we're interested in the difference between the estimator for the rank and the rank itself. And we can think about this or express this error in terms of all the errors made in the compaction steps. So here we use ml to denote the number of compactions happening at level L, and the random variable xil to denote the error or the sign of the error at the ith compaction at level L. So this could be +1 if there's a positive error of 2 to the L, or -1 if there's a negative error of -2 to the L. So the total error is exactly this sum. And this looks a lot like the kind of things we have seen how to bound using Chernoff bounds. And what we need in this case is a slightly different variant that I didn't talk about before, but it's in the book. So let me just state the special case we need here. So we have a bunch of independent random variables. All of them are bounded. So by some value AI, could be different for each of them. And we look at the sum of these random variables, assuming that the expectation is 0. So now the probability that the absolute value is greater than k is exponentially small in k squared, and the number we need to divide k squared by is the sum of the square of all the AIs multiplied by 2. So this is fact 1.4 from the book, basically, or a special case of that. Now let's go back to the sum we wanted to bound. So here the 2 to the L takes the role of AI in the lemma. So we need to bound the sum of all the AI squares. So that's this sum where we have 2 to the 2L in each of them. And we can rewrite this as ml multiplied by 2 to the 2L. So remember that's the number of compaction operations. And I claim that we can bound the number of compaction operations by 2 over c to the h minus L. So this is a claim we are going to get back to later. And now we have a sum that is clearly dominated by the last term. So that's because for each time L grows, this grows by a factor of more than 1. So it's a geometrically increasing sum, and it's dominated by the last term. So this is O of 2 to the 2h. Now let's denote the error by x. The probability that x is more than epsilon times n, we can upper bound that as being exponentially small in the deviation epsilon n squared divided by the sum of AI squared, which is 2 to the 2h plus 1. Okay, and now I'm going to claim, so this is the second claim that we need to substantiate, that 2 to the 2h plus 1 can be upper bounded by 4 times n over k squared. So if you believe that for a minute, the whole thing is going to be exponentially small in k squared divided by 4 epsilon squared. Okay, so we'll get back to this claim number 2 on the next slide. But before that, let's see that we achieved what we wanted to. So if you look at this, it's enough to choose k such that this fraction becomes larger than log 1 over delta. So, and to do that, we just need to choose it to be 2 times square root of log 1 over delta divided by epsilon. That gives us error probability delta. Now, before we move on, I would like you to think about what kind of delta suffices if we want a good rank for all queries. So in particular, we want ranks that are accurate within epsilon n for all queries. And I claim that we actually get this with probability, which is delta divided by epsilon. So let's consider the first of the two claims, saying that m of L can be upper bounded by 2 over c to the h minus L. We're going to do induction on h minus L. If h minus L is 0, we are considering the highest level h, and there have been no compaction whatsoever. So m of L is actually 0. So it's clearly true. So in the induction step, and I'm not going to be completely formal here, let's suppose that we actually know that m of L has the right upper bound, and then we want to increase, consider the level before, level L minus 1. And let's consider one level. The output of all the compactors of that level is the number of compactions times the buffer size divided by 2, because we do the compaction. So we can write that. So this is equal to number of compactions times c over 2 times the buffer size on the next level. And since we only do compactions when a buffer is full, this gives us an upper bound on the number of compactions at level L plus 1. Now consider m L minus 1. It should be L minus 1 on the slide. We can upper bound that by m of L times c over 2, and then by the induction hypothesis, this is upper bounded by the claimed amount. Finally, let's look at claim number 2. So we claim that 2 to the 2h is upper bounded by 4 times n over k squared. There are two facts we need to show this. First of all, at level h minus 1, each element corresponds to 2 to the h minus 1 input elements. Also, we know that at least k times c input elements have been at level h minus 1 because it was full at some time and we made a compaction and created level h. Using these two facts together, we get that kc times 2h minus 1 must be at most n. And this implies, in a couple of steps, that 2 to the 2h is at most 16 times n over k squared. So here the constant 16 is not what was promised, but it can be improved to 4. You can see the book for details. To wrap up the analysis of KLL, we need to analyze the space usage. The space is the size of all the buffers combined, and buffer L had size C of h minus L, k plus a constant, and which we can ignore. So, and if we sum of all of these, because we have a geometrically increasing series, it's dominated by the last term, so the size of the large buffer, which is k. So all in all, we get something that's O of k, where the constant depends on the choice of C. KLL supports merging. So given two KLL summaries, we can merge them into a summary of the union of datasets. And merging pretty much works like insertion. So we kind of push things up. So we start with level 0, merge the two buffers. If they overflow, we do a compaction and push up, and so on. So that's merging. All of this is time efficient, and this is because in expectation each input is thrown out after being in just 2 compactions. Every time it has 50% chance of being thrown out. So this means that the expected time we spend on each input element is constant. From a theoretical point of view, it's possible to slightly improve the space usage of the KLL sketch as we described it. Specifically, it can be improved to be O of 1 over epsilon times log of 1 over epsilon. So very close to the space lower bound 1 over epsilon. However, it's much more complicated, and also the sketches are not known to be mergeable. So there's a nice open problem there. Welcome to Approximation Algorithms and the lecture on ongoing algorithms part 1. My name is Rasmus Pagh. We'll start today by defining the key notion of competitive ratio. Then we are going to revisit the problem of scheduling job on parallel machines that we considered early in the course. Then we'll move on to bin packing, show a greedy 2 approximation algorithm, and also give a lower bound on the competitive ratio. Finally, we'll consider the online standard tree problem and show both lower and upper bounds. The competitive ratio is a measure used to denote the quality of online algorithms. Let up denote the cost of an optimal solution. Then we say that an online algorithm is C competitive if it finds a solution of cost at most C times opt. There's also an asymptotic notion of competitiveness. So an online algorithm is asymptotically C competitive if it finds a solution of cost at most C times opt plus something that's little O of opt. Here it's important that this are worst case guarantees for any kinds of input. So this must always hold. So basically, competitive here is synonymous with what we have called approximation factors previously in the course. So note here that the little O of opt is going to be negligible, so the approximation factor is basically approaching C as opt gets larger. We recall the problem of scheduling jobs on multiple machines. The input consists of a number m, which is the number of machines, and a sequence p1 through pn of processing times. In the online version, these are being revealed one at a time, and they are all non-negative. So this is the new thing compared to the setup that we have seen in the first lecture. Graham's algorithm, which is different from the local search algorithm that we saw in the first lecture, is a simple greedy algorithm that assigns each job to the machine that currently has the smallest load. If there are ties, they can be broken arbitrarily. So let's consider a particular configuration, in this example with m equals to 3. So the first 3 jobs are put on separate machines, and then we always put the next job on the least loaded machines. So it could end up looking something like this. Now, in order to analyze this, we can consider the starting time of the longest running job. Before this time, no machine can be idle. So this means that the starting time can be at most the average processing time, which is an upper bound by opt. Also, the length of the longest job is at most opt. So the total cost can be at most 2 opt. That is, the competitive ratio is bounded by 2. The factor 2 here is tight in the sense that it's the best constant that holds for any number of machines m. Next, we consider the bin packing problem in the online setting. So recall that an input to bin packing consists of a sequence of numbers, sizes of items, and now in the online setting these are revealed one at a time. Each item has a size which is in the interval 0 to 1. The objective is to assign these items to bins, and we can create any number of bins m that we want, such that in each bin, if we sum all the items in the bin, bj, their sum is at most 1, that's the capacity of the bin, and m is supposed to be as small as possible. So we have to arrange them in the bins so that no bin is overfull, and we have as few bins as possible. In the online setting, once we have assigned an item to a bin, we cannot change the assignment. An obvious approach is the greedy one. So the greedy algorithm always works on one bin at a time. And if there is room in the bin for the next item, we simply put the item number I in there. Otherwise, we seal off that bin and move on to a new empty bin. Now, I want you to pause and think. So I claim that the greedy algorithm has a competitive ratio of 2. And in fact, exactly 2. So this is both an upper and a lower bound. As you might suspect, the greedy algorithm is not the best one can do. One way of doing better is the so-called first fit algorithm. For an item I, we place AI in the first bin that is existing that has capacity for having item number I as well. If no such bin exists, we open a new bin and place AI in it. So in this example, the first 2 items go to the first bin. The third item doesn't fit in the first bin, so we place it in the second one. Fourth item fits in the first bin. Fifth item doesn't fit in the first or the second, so we open a third bin, and so on. In 1971, Jeff Ullman showed that first fit algorithm uses at most 1.7 times opt plus 3 bins. So that is, its asymptotic competitive ratio is 1.7. Also, the factor 1.7 is the best asymptotic competitive ratio that one can show for the first fit algorithm. How much can we improve first fit by being even smarter? It turns out that there are lower bounds for bin packing's competitive ratio that hold not just for first fit, but for any algorithms. So we want to show a limit on any online algorithm for the bin packing problem, not just a particular one. We're going to look at a particularly tricky input sequence. So let epsilon be some small number greater than 0, and look at an input sequence where we first have a bunch of half minus 1 size inputs. So that's called the number of repetitions m, and then a bunch of half plus epsilon. So also occur in m times. So after the first m inputs, we have placed these items in some set of bins. It's going to be somewhere between m half and m. So let's call this number m half plus t. And of those, 2t will have only 1 element in them, and the rest are going to have exactly 2 elements in them. So that's the only way we can achieve m half plus t bins. Now, in the second phase, we're going to be able to match 2t of these to bins with 1 element from the first phase. So 2 elements from the second phase do not fit in a bin, and the remaining m minus 2t are going to need separate bins. So now let's consider the competitive ratio after the first phase. So that is, after the first phase, we have to compare m½ plus t, which is the number of bins that we use, with the optimal number of bins after the first phase, which is m½ We can pack the elements 2 by 2. So we're going to use that ratio. Let opt m denote the optimum if we just consider the first m items. So if we work this out, it becomes 1 plus 2t over m. Now let's consider the competitive ratio after the second phase. Okay, so both of these are lower bounds on the kind of global competitive ratio of the algorithm. So after the second phase, we have the bins from the first phase plus the m minus 2t that got new bins, divided by m, which is the optimum, where we pair elements from the first phase with elements from the second phase. So in order to get a load of m bins. So here we get 3½ minus t over m. So now we have two lower bounds for the competitive ratio. One is increasing in t and one is decreasing in t. And we can see that no matter what t is, one of these is going to be greater than or equal to 4 over 3. So this is going to be a lower bound on any algorithm. This is an active area of research. In 2018, BARC et al. Showed that a competitive ratio of bin packing is between 1.543 and 1.578. In the final part of the lecture, we are going to consider the online Steiner tree problem. The input has two parts. First of all, there's a distance metric given by a weighted graph. This is given ahead of time, so it's not online in any sense. So we know this graph completely. Second, there's going to be a sequence T1 through Tk of terminal vertices. So these are the terminal vertices for the Steiner tree that we want to build. And these are given online one at a time. And the objective, as in the standard Steiner tree problem, is to output a Steiner tree that spans the terminal vertices, and we want to make the Steiner tree as cheap as possible. Here the restriction is that we can only add edges, not remove any, and we need to maintain the Steiner tree at all times. An obvious approach is a greedy algorithm that in each step adds the node or the edge to this tree that is the cheapest possible way of connecting the existing terminals to the new one. So simply choose the cheapest edge tij to some previous node tj. So first we add t1 to t2. For t3 we have two choices. We could either connect it to t1 or t2, and we are going to choose the cheapest one. So let's say it's the one for t2. For t4 we have three choices, and we choose again the cheapest one, and so on. The competitive ratio of the greedy algorithm is going to grow with the number of terminals k, as we'll see next. We consider a particular metric, which is the shortest path metric on a path of k vertices. So a simple path. So that is neighboring vertices will have distance 1. Distances that are, for example, 3 apart on the path will have distance 3, and so on. So t1 is just chosen at the end. And now t2 is chosen to be as far as possible from t1 as possible. So that's at the very other end of the path. t3 is chosen to be as far as possible away from t1 and t2. And so on and so forth. So we always choose the next terminal to be as far as possible away from the previous ones. Now in every step except the first one, there is some node, I claim, that has distance at least k over I plus 1 or divided by 2 to the previous nodes. And this is simply because if we look at the I plus 1 intervals of length k over I plus 1, one of them is going to be empty. So we can place the node in the middle of that. So this means that the total cost is at least the sum of these distances, which is k times the kth harmonic number, which is omega k log k. On the other hand, opt is clearly just including the edges of the path, which have total weight k minus 1. So the ratio between these two is omega of log k. Finally, we are going to give an upper bound on the competitive ratio of greedy. And the key lemma here is that essentially what happened in the previous lower bound is tight. So if we look at the ith most expensive edge that is chosen by the greedy algorithm, it's going to have a cost that is at most 2 times opt divided by I, which is up to a constant factor tight for the previous example. And a corollary of this is that we can now upper bound the cost of greedy by 2 times the harmonic number times opt, which gives us a competitive ratio of order log k, matching the previous bound up to a constant factor. To prove the lemma, we somehow have to relate the cost to the cost of the optimal Steiner tree. So let's draw the optimal Steiner tree here. And by definition, this has cost opt. Now we claim that if we take any set of terminals, it's possible to connect them with a cost that is not too far from the cost of opt. We can always create a cycle visiting these terminals that has cost at most 2 times opt. So this is the claim. So why is this true? Now we can use a technique that is a little bit similar to what we used when we consider traveling salesmen. So we look at the Euler tour around, which has length exactly 2 times opt, and we kind of take the ordering of the terminal nodes that we are interested in that corresponds to the Euler tour. The cost of going directly from one terminal to the next is bounded by the cost of the Euler tour because of the triangle inequality. If we have I terminal nodes and a tour among them of length at most 2 opt, it means that some of the edges, or at least one of the edges, has a cost of at most 2 opt divided by I. So finally, let's use this to give the last part of the proof. So let's order the terminals according to the cost incurred by greedy, such that the most expensive terminal comes first and the cheapest terminal comes last. So sigma is the permutation that orders them in this way. And now we're going to look at the first set of the I most expensive. So this is called Ci. And we are going to look at the cycle containing these. Now consider the cost T sigma I. It's less than or equal to the previous T sigmas, which in turn are chosen as the cheapest edge connecting to that vertex. So T sigma I is upper bounded by the cost of any edge within the I terminals. Now we can use the claim before, saying that there is some edge within these terminal vertices that has cost at most 2 opt over I, so that also bounds T of sigma I. So the cheapest in Ci has cost at most 2 opt over I as claimed. Welcome to Approximation Algorithms and the second lecture on online algorithms. My name is Rasmus Pagh. Today's lecture is going to be about matching problems. First, we're going to have a look at matching from an LP perspective, and then we'll talk about the online setting. We'll motivate it, show a lower bound for deterministic algorithms, and also show that the greedy algorithm matches the lower bound. This analysis is via duality. Finally, we're going to consider a fractional version of bipartite matching in the online setting. In the bipartite matching problem, we have a bipartite graph. That is, the vertex set consists of 2 sets L and R, for left and right, respectively, and all edges go from one set L to the other set R. So a bipartite graph can look something like this. A matching in the graph is a set of its edges that do not share any common vertex. So for example, the set of yellow edges I'm drawing now is a matching for the graph. The objective in the maximum matching problem is to find a largest possible set of edges that make up a matching. We can formulate this as an integer program, and we're going to make use of that later. So how do we do this? It's similar to what we have seen before. So we define a decision variable xe that is going to be set to 1 if e is in the matching and 0 otherwise. Now we want to maximize the sum of these variables subject to constraints that say that this is really a matching. To formulate this as a linear constraint, we sum over all the edges incident to a vertex v, and this sum needs to be less than or equal to 1 in order to satisfy the condition that there are no two edges incident to this vertex chosen. This has to be true for all vertices in L and in R. So delta v here is used to denote the set of all edges that are incident to v. Of course, as you know from previous courses, this problem, maximum matching, has a polynomial time algorithm. For example, you may have seen an augmenting paths algorithm. So why are we bothering writing this as an integer programming formulation? And the answer is that it will be a useful tool for analysis. So in particular, we are going to look at the LP relaxation of this linear program and its dual. So let's look at the primal and dual formulations of this LP. So the primal formulation is just as before. We want to maximize the sum of all xe, where xe is the variable that indicates whether e is chosen, and we want to make sure that at most one edge is chosen for every vertex, and all of these decision variables need to be non-negative. In the dual, we get a minimization problem where we minimize the sum of the decision variables pv, where we have a decision variable pv for each constraint in the primal. That is, for each vertex we have a constraint that basically, transposing the constraint matrix, says that the two vertices of a particular edge, vw, need to add up to at least 1. And here 1 comes from the coefficients in the objective function of the primal. Now, I would like you to pause and think. So how can we interpret the variables of the dual? Now let's consider what these LPs say about the original problem. So here, because we have a relaxation, any solution is going to be an upper bound on the integer solution, which is equal to the maximum matching size. By weak duality, the dual has the property that any feasible solution that we come up with, its value is going to be an upper bound on the optimal of the primal, which in turn is an upper bound on the size of the maximum matching. So the idea now is to use feasible solutions to the dual to upper bound opt. Now let's get back to the online setting. So in the online bipartite matching problem, we again have the two vertex sets. One of them, L, is given ahead of time. So this we know from the start, whereas the vertices in R are going to appear online together with adjacent edges. Each time a vertex in R appears, we need to decide which vertex in L, if any, we want to match it with. So for example, L might be given like this. A vertex appears with two edges, and we need to decide to match an edge. For example, we might match the first one. Next vertex appears, we match it. Next vertex appears, we are not able to match it, because we have already matched the vertex in L to another vertex, and we cannot change that matching. And it goes on like this. So we are not forced to match every vertex, so we can choose not to match a vertex to any of its adjacent vertices. Yeah, and that's pretty much it. So now the objective naturally is to create a matching that is as large as possible, and we compare the size to the offline opt. Okay, and we would like to obtain size at least c times opt, where c is as large as possible. So the rest of the lecture is about trying to optimize this competitive ratio c. One application of this problem is serving advertisements online. So in this setting, L is going to be a set of ads that need to be shown, that have been purchased, and R is going to be a set of web page views that come one at a time. And H indicates whether an ad may be shown to a particular web user based on things like geography, and maybe if you have information about demographics and things like this. And clearly, since we don't know what web pages are going to be viewed in the future, this is an online problem inherently. Now there are limits, as you can imagine, about how well you can do, and in particular for deterministic algorithms it's easy to see that they cannot do too well. So consider the setting where the first vertex in R is matched to two vertices, and we choose one of them. Then it can very well be that the next vertex may connect to the vertex that you have chosen, and then we have a situation where we find a matching of size 1, whereas a matching of size 2 does exist. So opt is 2, we get a matching of size 1. And in general, this can happen if we use a deterministic algorithm. It's always possible to come up with a sequence of vertices and adjacent edges that achieves this competitive ratio of at least or no better than 1/2. In terms of upper bound, there's an algorithmic technique which is usually the one we try first, which is the greedy approach. And in this context, the greedy algorithm would simply always add an edge to the matching if it's possible. It may be that there are several edges that we could match, but in that case we just make an arbitrary choice. For example, we might match to the first vertex. Now this is a deterministic algorithm, so the lower bound applies, and we can have a competitive ratio no better than 1/2, but as we'll see next, this algorithm is actually 1/2 competitive. The analysis of greedy that we are going to do goes via the dual of the LP relaxation. So the idea is to construct a feasible solution to the dual, let's call it P, of cost that is at most 2 times the size of the matching that we get. So 2 times the sum of all the XEs. Now remember that the dual wants to minimize the sum of all PV, where PV is a variable associated with V, under the constraint that PV plus PW is at least 1 for each edge VW in E. So we want to maintain this vector P at all times, and initially we can simply set P to 0 because we have no edges whatsoever, so all the constraints are void. So when greedy adds an edge, let's say from V to W, we need to update P to make sure that the constraints are met. And the way we can do this, or one way we can do it, is to simply set both PV and PW equal to 1. Now let's consider the size of the matching. Since we only increase the P variables when we add an edge, we know that the size of the matching is at least 1/2 times the sum of the PV variables. In turn, this is at least 1/2 times the optimal solution to the LP relaxation, which in turn is at least 1/2 times opt. So here we use weak duality and the fact that relaxation can only increase the objective value. So a competitive ratio of 1/2 is the best we can hope for deterministic algorithms, and we have a simple algorithm that matches it. Of course, you might wonder whether randomization can be used to get something better, to get a competitive ratio that is strictly above 1/2. It turns out that it's actually possible to get a competitive ratio of approximately 0.632, which is 1 minus 1 over e. Unfortunately, this is too complicated or too big a topic to cover in this class, but instead we'll cover a related result that kind of contains the gist of the result, which is about fractional matchings. So here we don't have to either choose an edge or not, but we can kind of split the matching edge between several of the outgoing edges from the vertex. Now this problem, as you might have seen, corresponds exactly to the LP relaxation of the original IP formulation. Let's look at an example. So we have L on the left, R on the right. We get a couple of edges, and it's possible, if we want, to split the matching half-half between the two. Now when the next edge comes, before we were not able to match, but now it's still possible to assign weight of 1/2 to this edge, because the first vertex V on the left hand side is only matched halfway. Okay. So the rest, if there's only this outgoing edge, we cannot match. We can choose to match the outgoing edges unevenly. Of course, it can also happen here that there's no way to add any weight, since the vertices on the left hand side are already fully matched. Okay, so the sum of the corresponding decision variables is 1. We're going to study a very natural and simple algorithm for this problem called the water level algorithm. So here we think about each vertex as on the left as kind of a container able to hold at most 1 unit of water, so corresponding to how much they are matched. So basically each of them we can imagine a small container. And whenever a vertex comes on the right, it basically has 1 unit of water that it can distribute among the vertices that it has edges to. So we somehow need to pour up to 1 unit of water to the adjacent vertices. Or maybe it's beer, because I'm going to draw it in a nice yellow color. Okay, so here we could, for example, split it 50-50. When the next edge comes, we can only pour half a unit here, so we're kind of going to get half a unit left over, and so on and so forth. So there might be a case where the adjacent vertices do not have the same amount of water in them. In this case, we always fill into the least full first. So we're going to first fill the third vertex, and then we're going to split the rest so that they end up at the same level. So this is the water level algorithm. It's instructive to also have a look at it from the side, so to speak. So if we think about a vertex W with 1 unit of water and look at all the neighboring vertices, when we start, they might have different levels of water in them. And now we're going to pour first in the empty neighbor. When it's as full as another neighbor, we start pouring in several at the same time. And at the end, all the neighbors that we have poured to are going to be at the same level. So this is the water level, so to speak. So all containers that have received water from W are going to have the same level, which is less than or equal to, or actually equal to the water level. So if there's some container with a higher level, let's call it YV, it won't have received any water. And in particular, this means that all the neighbors that received water have a level less than or equal to YV at the end of the pouring from W. To analyze the water level algorithm, we're going to take a similar approach as before. So again, we want to consider these LP and the decision variables XE, where XE is now a fractional weight of an edge E. And basically we want to bound the LP value by some feasible solution to the dual. So what we did before was basically whenever we set a decision variable to 1, corresponding to an edge VW, we set PV and PW equal to 1. So one possible way of generalizing this would be that if we set xe equal to some delta, we could set pv and pw also equal to this delta. Or maybe even smaller, right? Because we are looking for a cheapest possible solution to the dual. Right, so let's look at an example of how this might work out. So water level is going to split things 4-way here, and we update the dual variables also drawn in blue. They are all going to be 1/4. Now comes a new vertex with 3 neighbors, and we water level is also going to split 3-way 1 unit of water, and we update the duals. Then there's a vertex with 2 neighbors, and now we're actually going to fill up the corresponding neighbors with whatever capacity there is, and we're going to have some spare water, so we are actually only going to fill 5/6 units of water in. And then finally, okay, so these 2 last are full. Finally, we have a vertex with just a single neighbor, and it doesn't have any capacity, so we're actually not going to be able to pour any water into its neighbor, because the dual constraint is basically tight. So this kind of means that there's no hope that we can get a better constant than 1 in front of delta. So we're not going to be able to get any competitive ratio that is strictly above 1/2. So somehow we need a better way to find a smaller solution to the dual in order to get a better bound on opt. And yeah, the idea is to kind of deviate from what we did before, which was kind of splitting the amount by which we increase the dual variables evenly, and now we are going to do the split unequally. We can think about increasing variables PV and PW as also pouring water into containers associated with those, and before we poured equal amounts into PV and PW and a total amount of 2 units of water. And now we hope that we will be able to get by pouring less water. And the way we are going to be splitting it is going to be controlled by a function g, which is going to control the rate at which water flows to the vertex in L, so v. And this is going to depend on the current value of the dual random variables. In the notes, they describe how they come up with a good choice of g, and I'm not going to cover that. But in the end, what they come up with is this function. So it's an exponential function that increases with the level. So basically, when the level is 0, the rate of filling is going to be e to the -1, and when it's almost full, the rate is going to be e to the c-1, where c is going to be the target approximation factor. Of course, if this is the rate at which water flows to v, then water is going to flow to w, its neighbor, at a rate which is 1 minus g of pv. So let's wrap up the analysis. So there are 2 things to do. So first of all, for every edge, v, w, we need to be able to argue that the sum of the dual random variables is at least 1, because if this is true for every edge, v, in the graph, this gives us dual feasibility. There are 2 cases we can consider. One is where the vertex v is full at the end of the water level algorithm. So in this case, we are simply going to lower bound the sum of PV and PW by PV, and the value of PV is simply the integral from 0 to 1 of t of z, where z indicates the current level of water. In the case where the vertex v is not full, so that is why v is strictly less than 1, at the end of the water level algorithm, we give a slightly more complicated bound. So first of all, we integrate up to yv, so that's the contribution to pv, or that gives us the exact value of pv. And then we have to lower bound the value of PW. And we don't know exactly how much has been added to PW, but we do know that whatever was added is more than whatever would have been added if the neighbors had level YV. And this is because G is increasing. So the rate is lower bounded by 1 minus G of YV. And since YV is less than 1, we know that all water from W was used, so we integrate from 0 to 1. And now we can insert the guess from before of G of Z, e to the CZ minus 1, and a bunch of computations, essentially high school integration, tells us that the choice of C, which is 1 minus 1 over E, actually works. And an amazing thing is that this happens to actually be the best competitive ratio. So there are lower bounds also that show that it's not possible to do anything better than 1 minus 1 over E. In the randomized case, it's possible to do something that is analogous, where essentially these fractional matchings correspond roughly to probability distributions over choices of edges.